Welcome to 2.4, Sketching Graphs of Rational Functions. This is our last lesson in the unit, so this is a bit of a summary, and you will be getting a quiz just coming up shortly after this one, so get ready afterwards for the quiz. The whole point of this lesson is sketching graphs of rational functions without technology. So once again, we will not be using graphing calculator or the computer with graphing software during the quizzes or the tests, but you can use them during this lesson to check your work. So if you have a TI-83, that's great. If not, you can go online and you can download an app for your phone, or you can use desmos.com or geogebra.org, and those are excellent online graphing calculators. The getting started is really an example of what we're going to be doing this whole lesson is sketching graphs. So the key for sketching graphs is, first of all, looking at the non-permissible values of x. So that would be step number one, is the non-permissible values of x. And if you remember, that turns into, once you find them, non-permissible values are going to give you either the vertical asymptotes or the holes. So the first step would be to look for the vertical asymptotes or holes, and we'll see, or we'll remind you once again how to differentiate between those two. Next would be to look for the horizontal asymptotes. That would be the third step. And then step 4, and I guess the order doesn't matter too much here, you can look for the x-intercepts, and 5, y-intercept. And then at the next point is to sketch, make a table of values. And specifically, your table of values should be investigating values just to the left and right of any of the vertical asymptotes. So we'll be taking a look at that. Pardon me. So even though the getting started doesn't have you do all of these steps, because it doesn't say sketch the graph, it just says determine the non-permissible values of x and the intercepts. So really it's kind of doing 1 and 2 and then 4 and 5, but we can just go ahead and consider the getting started as one of the examples. So let's try to graph this. So first of all, how do you find the non-permissible values of x? So the non-permissible values of x are when you're breaking a rule of math. There's no square roots going on here, so there's no square roots of negative values, but there is a division here. So you're going to wonder, when will we be dividing by 0? So the non-permissible values of x here, maybe I'll switch to a different number here. The non-permissible values of x, non-permissible value, how about NPV? The non-permissible value is x cannot be equal to 0, right? Because if you've got a 0 here, you'd be dividing by 0. Now, if you recall, when is this a vertical asymptote and when is this a hole? It's a hole when the numerator and the denominator have a common factor and you end up factoring out that non-permissible value. So it doesn't happen in this case. If you could factor out an x on the top and the bottom, then x could not be equal to 0. It would be restricted from its domain and it would be a hole. In this example, however, it is a vertical asymptote. So we can say a vertical asymptote at x equals 0. So first of all, we know we're going to get that dashed vertical line right at x equals 0. There are no holes, none, because that is the only non-permissible value and is not factored from the numerator and the denominator. Now, looking at the horizontal asymptote, if you recall from a previous lesson about the horizontal asymptotes, is you look at the highest degree in the numerator polynomial and in the denominator. So here it's a 2, right, and there it's a 1. So you can think of this as just the same as when you have an x over just a number. We will not be getting any horizontal asymptote. Oh, hold on a second, I'm just going to pause. Okay, I thought I would just review the horizontal asymptotes just for you. Now, this was from the notes that I gave you off of the flipmath.com website. So here, if I go like this, I can write on here, and if the power on the bottom is bigger, oh, did I not do that right? Sorry. There, if the power on the bottom is bigger, then you have an asymptote at y is equal to 0. If the power on the top is bigger, you do not have a horizontal asymptote. And if the powers are the same, then the horizontal asymptote would be, well, y is equal to, I'll say a over b where a is the coefficients of the highest power in the numerator, and b is the coefficient of the highest power in the denominator. So if we're to sort of go ax to the n in the numerator, and then bx to the same number n on the denominator, and this is the highest power where n is the highest power and a are the coefficients, then the horizontal asymptote is y is equal to a over b. And I'll just add that one note to this is that if the power on the top is 1 bigger, so power on top is, we'll run this, if power on top is 1 bigger, it's so hard to write with this. There's no horizontal asymptote, but there is an oblique asymptote. Then oblique, and so and again, an oblique asymptote is at an angle. Okay. So we do not have to actually find, for our exam and for our tests, we don't actually have to find the equation of those oblique asymptotes, so I will actually be telling you to disregard some questions, but I just wanted to add that note because you should be able to recognize that. Okay, so if I flip back, I guess I lost what I had done over here. So let's continue on with this one here, and I think we had written already that our vertical asymptote was x equals 0, no holes. Horizontal asymptote, none, because the power in the top was higher. Now let's consider our x-intercept and the y-intercept. If you're like me, and sometimes you kind of forget which is the x-intercept and which is the y-intercept, if you just draw the x and the y axes a little bit. So the x-intercept is going to be some point that lies here. So when you think about what that means, the point, and when we make the points, this is the x value first and then the y value. This will be some number x, right? And then the y value will be 0. So this is what an x-intercept looks like. So in other words, an x-intercept is, what's the x value when y is equal to 0? So they're pretty easy to think about then. You think, oh, okay, well, when is this going to be equal to 0? So when will the y value be equal to 0? Normally what you say is, well, when will the numerator be 0? So if I factor that numerator, the x-intercepts typically involve finding the zeros, we call it, and you can factor the numerator. So we get x plus 3, x minus 3. A little messy, but I think it'll work, and then all over 2x still. Either of those expressions will be 0 when either x is plus 3 or negative 3. So my two intercepts will be negative 3, comma 0 is my first one, that's a comma, and my second one is positive 3, comma 0. So I have two x-intercepts. My y-intercept, so what's the y-intercept? So here I'll put a dot for a y-intercept, and so the y-intercept, you can see it's when the x value would be 0, and then we have to figure out what the y value would be. So plug in a 0 for x. So if we put in a 0 for x, we'd have 0 squared minus 9 divided by 2 times 0. So we'd be dividing by 0. So we would say none here. So now we're going to make a little sketch of this first one and see what we have so far. Maybe I'll switch to having a line instead. Okay, so there'll be my one axis, my other axis, and if I were to make a, you know what, a dashed line, maybe I'll make it green for my asymptotes. So I have a vertical asymptote at x equals 0, so I'll add that little green line over there. I don't have any other asymptotes, and I don't have any other holes. I have an x-intercept at negative 3 and at positive 3. Okay, and so I don't really know too much about what this graph is going to look like, but I do know that the behavior on the left-hand side and the right-hand side of this vertical asymptote, it'll be approaching either from positive infinity or negative infinity. So on the right-hand side, it'll either look like this, right, or it'll look like this, one of those two. I don't know which, and that's where I bring out the table of values. So my table of values, I would go, okay, so I make an x and a y. and I'm interested in, so just beside 0. So I can put a positive 0.1, so that's just to the right of that vertical asymptote. And I'm wondering, am I going to get a positive value or am I going to get a negative value? So I can go over here and say, okay, if I put 0.1 in here, 0.1 squared is a very small number, it's 0.01 minus 9. So the numerator is essentially minus 9 divided by 2 times 0.1, which is 0.2. So I'm going to get a negative divided by a very small number. I'll get a negative value. And it turns out to be pretty close to negative 45. So negative 44.9, I think what it is. So it's coming down from the bottom. So I'll get my eraser out. And it's going to be coming from that way. And now I can say, well, it's got to be going through here. Now I wonder about this this 0. Is it a multiplicity of 1 or an odd number? Then it'll be crossing. If it's an even multiplicity, it'll be touching and coming down again. And when I'm looking at it, that comes from this factor right here, the x minus 3. It's not squared. It's an odd multiplicity because it's to the power of 1, so it's going to be continuing on like that. And there's probably a curving feature. So we'll take a look in a minute. Make sure you put arrows on either side of that. And then we'll take a look on the other side of negative 1, so of x equals 0. So we'll say negative 0.1. So I'm just going to test putting a value in over there. So if I put negative 0.1 squared, I'll get a small positive value, minus 9. So my numerator is pretty close to negative 9. Divided by, now I'm dividing by a negative, so I'll have a negative divided by negative. So I'll get a positive version. If I type it in my calculator, I think I get something like that. So again, I wasn't quite sure. On the left-hand side of this vertical asymptote, was I approaching positive infinity or was I approaching negative infinity? I was approaching positive infinity, so it's going to come down like this, and I'm pretty sure we're going to get a shape like over there. So at this point in time, it would be good to go and check your work using a graphing calculator or some type of technology. So if I pop over here, I can get rid of that now. If I pop over to this Desmos, here is my x squared minus 9 all over 2x. It does not put in my vertical asymptote, but there it is. So that works out quite well. I'm not going to do a whole bunch of other examples. If I walk through this, did I lose my one with all the pictures in it? There it is. I'll undo that. Now if I walk through here and take a look at the other examples, on the next page is a summary. This is like what I was saying before. To sketch the graph, find the non-permissible values of x. Some of them will be holes, some of them will be vertical asymptotes. Find the equation of the horizontal or oblique. In fact, we don't have to figure out the equation of an oblique asymptote. Find the behavior of the graph near the asymptotes. That's what we did using our table of value, and find out what the intercepts is and then sketch it. So here's a nice example of sketching a graph with a hole. They work through the example, and I'll just have you note that the denominator is 4 minus x. So they change that to x minus 4. The relationship between 4 minus x and x minus 4 is that they are opposites. So when you make that switch, you've got to introduce a negative sign. Okay, so it would kind of be more sensical if you put the negative sign in the denominator, but you can put it in the denominator or the numerator, or you can put it out front. The key is you have to put one negative sign somewhere in all these terms that are either multiplying or dividing. So when you switch from 4 minus x to x minus 4, make sure you put a negative sign, and it does make sense kind of to put it in the numerator for when you're making your table of values. At that point, they cancel out your x minus 4's, so that non-permissible value turns into a hole. There's going to be a hole at x equals 4. And just a reminder that the next step, students always fail to do the next step, you should figure out what the y value is associated with that hole at 4. So you go back to this form of it, either or negative left parentheses x plus 3, or if you distribute the negative sign, negative x minus 3, either place you put in that 4 and then find out what your y value is. So minus 4 minus 3 gives you this minus 7. So that's where the hole is. Here they put the hole, and then when they sketch this line, negative x minus 3, there's the hole. All right, well, why don't I do the check your understanding value question with you on this one. Nope, I want to go like this. Okay, so the first step, I'm going to say, oh, I'm going to switch this, right? I'm going to change this to x minus 1. So if I go y is equal to, like this, I'm going to change this to x minus 1. But this is the opposite of this, right? In the numerator, can we factor that? I think we can if we say x minus 4 and then x minus 1. I'm saying, hey, look at that, common factors on the numerator and denominator. So when I do that, at the same time, I need to restrict the domain, because I can always divide the numerator and the denominator except for if I'm dividing by 0. So when would I be dividing by 0? When is x minus 1 equal to 0? When x is equal to 1. So this definition of the function is identical to y is equal to x minus 4 only when I include this restriction in the domain. Okay, so this statement here is mathematically identical to this y is equal to x minus 4 only if I add this restriction. Okay, so like when you're solving algebra and you say, well, as long as I do something to the left hand side and do it to the right hand side, then it's still equal. This whole polynomial function here, rational expression, is the same as this one only if I put comma x is not equal to 1. If I don't add this piece, I've left something out. Okay, so now I've got this negative in the denominator, so I'll say y is equal to negative x minus 4, very similar to the example that I just did with the restriction that x cannot be equal to 1. So y is equal to negative x plus 4 with x cannot be equal to 1. So clearly I'm going to have a hole, so I will have a hole at my x value has already been figured out as 1. So what's my y value? If I put a 1 here, negative 1 plus 4, that would be 3. So now when I make my sketch, there are no vertical asymptotes. There are no horizontal asymptotes because it's simplified into this linear equation. I don't have to do a table of values. It's really not too hard. My y-intercept will be 4. So I'll label that one right there. I'll try to label that one right there. And I get a, here I'll make a line again. So I get a line with a negative slope. So it goes like that. It dashed it on me again. I shouldn't do that. I should make it solid to see if I can get the line over top. Wow, pretty close. And there is my y-intercept. And at 1, 3, so when x is 1 and y is 3, there should be a hole there. So really, I should get my eraser out, make it a small little eraser, plop a little hole in there. Oh, it doesn't work very well. Well, I'll pretend I'm doing a hole, so the hole would look like a circle. Okay, so on your pen you go like this, a hole, and then you like this, and don't forget to put your arrows at the end like that. So there we go. There is our example. I'm going to keep this video short. I won't be doing too much more. Example number 2 is sketching a graph with horizontal and vertical asymptotes. We would sketch this graph, follow the same steps. I'm going to continue on. Example number 3 you do not have to do because it's an oblique asymptote, so you don't have to worry about that. But example number 4, let's see if we can get to it. Let's just do example number 4. Sketching a graph with asymptotes and a hole. So when does that happen? Well, looking at this denominator after they factor it, and they got 2x plus 3 and x plus 3. 2x plus 3 is common, so you're going to have a hole when 2x plus 3 is equal to 0, or in other words, when x is equal to negative 3 halves. And you're going to have a vertical asymptote where an x is equal to negative 3. So there's 2 non-permissible values, right? One of the non-permissible values is x is equal to negative 3, turns into a vertical asymptote. The other non-permissible value turns into a hole because of it factored from the numerator and the denominator. They make their vertical asymptote at the correct spot. They figured out the y value when x is equal to negative 3 halves. It's 2/3. So this is that x and that y value, not very clearly marked, but they certainly have the scale marked on their axes. And then they probably use the table of values to check just to the right of that asymptote, was it positive or negative? And just to the left of that asymptote here, if I scroll down a little bit, so the asymptote is at negative 3, So they said, oh, what about just to the left of it, negative 3.01? Oh, I get negative 100, so I know it comes from the negative infinity. And over here, just to the right of it, positive infinity. And now this is their way of testing what happens as we make x approach a very large number and a very large negative number. And we have a horizontal asymptote at the x-axis, and you'll notice they didn't draw it. This is another place where our textbook fails a little bit. You see, they write it in text that the horizontal asymptote is at y is equal to 0, but they don't actually put it in there. So I would like you guys to actually put in this horizontal asymptote in here that they failed to do. Okay, so, and just a reminder, the other thing that they often fail at, or consistently fail at, is they forget to put the little arrows in there. So we can do better. So we're almost done the video. What I'd like to do first then is to do a number 4 to sketch the graph of this rational function, then state its domain and its range. So first thing we'll do is, hey, I just can't let that denominator sit there because it's jumping out at me. This is a difference of squares, isn't it? So that's going to be an x plus 3 and then an x minus 3. And then it's like, oh, it's like a puzzle that undoes itself. I'm going to stroke like that and like this, and at the same time say, therefore, x cannot be equal to, well, when am I dividing by 0? When x is not, when x is negative 3. So in other words, I have to restrict that and say, I'm not dividing by 0 because I just stated I'm doing it for all values of x except for when x is equal to negative 3. So now, just to clean it up a little bit, I get 1 over x minus 3, and x cannot be equal to negative 3. So let's consider here. We have a hole at, and x is negative 3, comma, what would my y value be? So if I put a negative 3 in there, 1 over negative 3 minus negative 3 minus 3, so it's 1 over negative 6, or negative 1/6. So there's my hole. I won't have any, I will have a vertical asymptote at x equals 3. My horizontal asymptote reminds me a lot of 1 over x, right? Y is equal to 1 over x. I kind of think of that as a parent function. We'll be talking about that kind of a parent function. So it looks like 1 over x looks like that, and it has a horizontal asymptote at y is equal to 0, or just by following the rules, if the power in the denominator is bigger, you're going to have a horizontal asymptote at y is equal to 0. The intercepts, are we going to have any x-intercepts? Is there any way I can make a 0 in the numerator? None. So there's no x-intercept. The y-intercept, if I put in a 0 for x, I get 1 divided by negative 3, so I get negative 1/3. Okay, so I'm pretty close, pretty ready to well, this is a solid line again. So I'm pretty ready to sketch something. And now I'll switch to a dashed line so I can put in my vertical asymptote at x equals 3. So this is at x equals 3. Okay. I have a hole at negative 3 and negative 1/6. So here I've got a little hole there. Is there anything else I have in here? Oh, I have a horizontal asymptote. Okay, so going back over here, I've got a horizontal asymptote at y is equal to 0, so it kind of goes right over top of that. If I did it a different color, perhaps it would work out better. And a y-intercept is 0, negative 3. I forgot to put that one in. So 0, negative 1/3. So it's a little bit lower, isn't it? So it's going to be going through there. Oh, darn it. Going to be going through about there. Okay, so to the left of the this vertical asymptote, I suspect it's going to be a very large negative value, and to the right of it, I don't really know. So I'm suspecting that my sketch is going to be looking like this, right? Because it can't cross this horizontal asymptote anywhere else. Not a great sketch, but it kind of goes like that, right? Now on the right-hand side of it, I don't know. It could be going here, or it could be going like there. So how do we test it out? Well, we know we have a vertical asymptote at 3, so what happens if we plugged in a value of, say, 3.1? So looking at 1 over 3.1 minus 3, I get a positive denominator, right? So a positive divided by a positive, so it will end up going like this. Okay. And that reminds me that, remember this parent function, I said that 1 over x minus 3 looks a lot like 1 over x. The parent function looks like this. So this x minus 3, all that happened was it got shifted over to the right 3. Okay, it looks a little bit stretched at the same time, but that was probably my drawing. Let's go see what desmos.com says about this one. So let's remember it's the x plus 3 one. There we go. So I'll get rid of this one, and it's my last one, number 5. There is my x plus 3 over x squared minus 9. And you'll notice it doesn't really show the hole, does it? So one of the holes was where x was equal to, where was it? Over here. Let me see if I can find a x equals... Oh, there it is. Okay, so it doesn't really show the hole unless you find the mouse right over top. So you notice it does give me an open circle when I do that. Oh, so as I move over here, see if I can, there. So it's an open circle right then. So that would be how I would want you to graph it. Plus, I would want you to be drawing a vertical asymptote and a horizontal asymptote. Okay, so your homework will be. Oh, let me find the right thing. So okay, I'll get rid of that. So. To work on for homework, I'd like you to avoid the questions that have the oblique asymptotes. So when you can do from questions 3 to the end of the A and B section, except for, I'm just looking here, I believe that 3D, no, is it 3? No, it's 5D, pardon me. So 5D you don't have to do because that's going to give you an oblique asymptote. Good luck, and we'll talk to you later.